So under normal circumstances, what do you expect? With compression, with pressure being applied there, what's supposed to happen? The cork the cork stopper is supposed to widen, isn't it? But why does it thin out instead and fly out of the bottle?
I try, madam.
Pardon?
I try because pressure is only applied on one side.
Not really. Pressure can compression, just like tensile forces also, they can also be applied on one side only. So imagine imagine there's bread on the floor. Can we please mute our mics if we're not speaking? So imagine if you step on bread on the floor, you only applied pressure from your shoe one way, isn't it? But it will still compress.
And the pressure builds up inside there.
Pardon? Hello, can you please repeat what you said? Unfortunately, I didn't get what she was trying to say. But anyway, let me quickly mention that. So the material that the cork stopper is made out of, okay, that cork material, it's actually the only material in the world that thins out, okay, when compressive forces are applied on it. So the cork material, what happens is that when you apply those forces on it, instead of going out in the sides, that type of material actually thins out. And it's the only material in the world that does that. Okay, that's why it's used for wine bottles. That's one of the main reasons why. The type of material that it is, it does the opposite. So usually for most materials, when you hit on them, they're supposed to spread out in the sides. But with cork material, when you hit on it, apply a force on top of it, if it's on the floor, it actually bounces up. Okay, it kind of spins out with that force. So we'll look at that a bit more in detail. When we look at the various materials, we'll look at it again, but that's the reason why. It's actually because of the nature of the material being cork in this case. Okay. All right, so this is a compression test setup. That's how it, so if it was cork, it will not move in the sides, okay? It will actually resist these forces and it would try to thin out in that direction, but it will never thin out in the sides. I mean, it will never spread out in the sides. That's the nature of that particular material. Okay, so coming to the shear and torsional tests, the shear forces we looked at, more like a twist, okay, or a movement, the slide. Okay, it may not really be, it can be a torsional movement in this case, where you have the tangential forces at play. Okay, the T is there. That's where you have more like a twist happening. Okay, or it can just be like this where you have a base. Okay, then there's that sliding movement happening. Okay, and there's that movement that has happened at a certain angle theta there, as you can see. Okay, so meaning the forces were applied over there and there. So that's a cross-sectional area A0 happening there at the top. So this is the formula. So for stress, whether it's shear stress, what is always force over, except for strain. Stress will always be force over cross-sectional area all the time. Please don't get confused. I need you to understand this part. It's always like that, even in life. Okay, when you put pressures, we like to call them pressures, they're forces. These forces are actually applying where? They're being applied on your brain. And when these forces are too much, you feel like your brain can't take it anymore. So it's the same, this formula applies everywhere. The general formula, stress When you say someone says, I'm really stressed out, this stuff is stressing me out, it means there are certain forces being applied on a certain area. Okay. And you need to remember this, please. What changes is the different types of forces. I mean, the different types of stresses. However, the general understanding remains the same. Okay, and the types of forces maybe will be changing here. Otherwise, this is the general understanding of what stress is basically that it's force over a certain cross-sectional area. Okay, so there we have. So with shear stress, I do not even bother so much with problems, okay, to do with calculations, to do with shear strain, but I always require that you should know the definition at least. You should have an understanding, you should be able to explain what shear strain is. So we come to finally reach our strain stress curve. This is how it looks like. So what do we have here? We have the y-axis and we have the x-axis. On the x-axis, we have strain. On the y-axis, we have stress. Okay. Sometimes what we can have is the extension, force over extension curve. So sometimes you can use the force will be on the y-axis. I think that's common in usually in past papers, you find that force will be on the y-axis and then the x-axis will have the extension. So they change in the L value. It will be here usually. And then you calculate to find stress and whatnot. So, or it could just be stress and strain as it is. So this is how, that's the curve going up and like that. Okay, so depending on the material, how hard it is, how tough it is, okay, usually it will come from here and to be shorter than that, okay, or this angle would be less steep than this to maybe come down like that and then do that curve on top. But generally, this is how it will look like. Okay, so for a metal, that's how it will look like generally. For polymers, there'll be this part, elastic region will be higher, and this part will be shorter. So this part of the curve is known as the elastic region. Okay, and this part of the curve is, actually this is not even a curve, it's a straight line. This is a linear part. Then this part of the curve is known as the plastic region. So briefly, just to help us understand, when you get your specimen, place it on the machine, this machine, okay, and you begin to apply those forces, you begin to apply stress. Okay, so you have strain working in that movement and stress being applied. Okay, let's see what you're applying. As you're applying it, it's coming there, okay, stress against strain. You have the values there. So what it means is that where you have this straight line, the linear part of the curve, this part here, the straight line, what is known as the elastic region. What it means is that forces that are applied in this region, okay, whatever stress is applied in this region is not permanent. Okay, just like the elastic band, when you get your elastic band, put it in between your fingers and stretch it out a bit, it will retain its original shape. Okay, that's what happens even with metals, not just polymers or elastic materials, but with all materials, except the degree of or the size of the elastic region is what's different, with what varies. So for metals, they're able to retain their shape quite well. Okay, depending on the stress. They'll stretch out a bit, you will not even see it actually. It's not even that easy to see with your naked eye, but it will return to its original shape. It's easy, but what it means is that after this place, the yield point, what is known as the yield point, beyond this point, okay, where you have now this curvy part coming in, or the plastic region, under this region, it means that whatever deformation happens here is permanent. Okay, so here in the elastic region, it means that deformation that takes place here is not permanent, while the deformation that takes place here, or the elongation that takes place here is not permanent, while the elongation that takes place here is permanent elongation. And then you have your fracture here. So it means now as you, so what happens, you see what's happening now as you're going this way, the stress is decreasing, isn't it? Necking is happening. So the necking will happen here from the maximum load. From this point here, that's the maximum. Okay. This is the maximum amount of stress, the total stress. This is the maximum amount of stress that your material can take before it begins necking. Okay, that's the maximum. So after this point, you experience that decrease in stress, right? And that's where your necking is happening, right up to this point where you have fracture. Okay, and then your material will snap in the middle. Your specimen will snap in the middle. So this 0.2% offset can sometimes be 0.1% offset. So this offset is really meant to determine, okay, it's an allowance for this yield point. So on the curve, it's not that easy to see. So we always put a percent and offset, okay, usually 0.2% in this case. That's the offset that we usually place for this Y here, the yield point, the point that separates the elastic region from the plastic region. So these are generally those, but when you look at other literature, okay, they'll go in detail. So every part, even just here, there are so many things that happen and there are so many names here, about 3 names just at this point. Just here also, there are about other 5 names here that come up. But for you, this is enough, basically. You don't need to know beyond this. We'll stick to this level. Okay. So just to understand which part here is happening at which part of the, just to understand what is happening at which stage, okay, of the tensile stress. This is how it would look like. Okay, so you have your curve. That's the Y, the yield point. That's separating the elastic region, that's below, from the plastic region. Okay, the plastic region is a place where you have the permanent deformation. Okay, so you have in this region, that's what you get. Huh? You have the initial length, then you have that length elongation happening there. So it means beyond this, you have now that. Whatever deformation is happening here is permanent. Okay, right up to this point where you have that fracture there. So this is known as post-uniform elongation. Okay, after the ultimate tensile stress, or the TS, or the UTS as it's sometimes called, the ultimate tensile stress point. So beyond this point, you have the necking there beginning, like I said, and then up to the point where you have the fracture happening there. So as stress increases, the point in the linear relationship is finally reached when the material begins to yield, okay? So it now begins to yield the stress. To yield means to succumb to something. To yield to something is to succumb to something. So it begins now to yield to the stress, okay? It can't take it anymore. So it means now the stress begins to permanently affect the physical properties of the material. So that's why it's known as a yield point. The change, so it can be identified by the change in slope at the upper end of the linear region. I already explained this. So the yield point is also known as the yield yield stress, or the elastic limit. Okay, so elastic limit in that beyond this, whatever is happening this side now in the plastic region is now permanent. It's now permanent. Any examples of materials that enter the plastic region? Any examples? Can you think of something that you feel maybe behaves in that way, where the plastic region is reached and this particular material begins to has undergone some permanent deformation? Brian, Alex, Edward, any examples?
Even, madam, we can pick on the even just the material that you use to make hose pipe.
Uh-huh. Yes. Click on that one. Yes. So what happens?
Like we had put it, if you stretch the hose pipe,
Mm-hmm.
it will elongate at some point, but if you continue pulling it,
Mm-hmm.
it will enter the plastic stage where even it change color, you see that
Yes.
the plastic stuff, it will look white.
Mm-hmm.
And once it reaches that, it can't be restored to its original length,
Yes.
meaning the distortion becomes permanent at that stage.
Yes. Yes. Thank you. That's a good example. Even ladies, I think can agree with me. When you buy a rubber band, oh, not a rubber band, but a hair band. When you buy a new hair band to tie your hair, the first few weeks, it will be excellent. It will be like tying your hair so well. Then what happens after like 3-4 months, provided you use it every day? To become loose, isn't it? So it means that the elastic material in that hair band have reached some limit somewhere, okay? They've entered the plastic region. So meaning that stretching now, okay, that increase in length, they were initially able to bounce back to their original length. But over time now, those hair bands, what happens? They just become loose. If they used to go around your hair like twice, you have to let them go your hair like 3-4 times just for them to hold your hair. Something like that. Okay. Also back in the day, I remember young boys would be wearing shorts. You find a boy, these days, I think you'll never see such things. You find a boy, especially in the compounds, walking while holding his shorts. That short, it probably means that when the mother bought him those shorts, they used to hold his waist properly. But what happened over time? Some plastic deformation was reached, huh? And the waist of the shorts was permanently elongated. Okay, so meaning the material in those shorts, the elastic material in those shorts, in the waist of the shorts, reached the plastic region, huh? And there was a permanent elongation such that now the waist now was enlarged. And now the poor boy has to walk while holding his shorts in his hands. Something like that. So there's so many examples, there's so many things that we deal with that undergo that change. So stress applied to a material, it won't be uniform, like tensile strength will not be uniform on both ends. So one end will probably pull than the other. So it means that the fracture will not happen at the center. Okay. So where will the fracture happen? Where there's more force or where there's less force? Which side will it favor? What do you think?
Come again, madam.
So we say that for tensile strength or for tensile stress, if stress or force is applied uniformly on both ends, the snapping or the breaking will happen where? At the middle, isn't it? At the center of the specimen.
Yeah, the center.
So now let's say that the forces applied were not the same, they were not equal. There was one force that was much greater than the other force. Where do you think in that case the snapping will happen, or the breaking or the fracture? Where do you think it's going to happen? In which region? The region where you have the less force, or in the region where you have the higher force?
I think it snaps where you have at the region where you have higher force.
Do we have those that think otherwise? Charity, you're trying to say something?
I was saying the region with the higher force is the one to snap.
Really? Okay.
That's what I think.
Okay. All right. Okay, so there are two regions that are very important, okay? The elastic and the plastic region. So here we also use Hooke's law. The fact that we have elasticity being talked about, we need to go back to our high school notes, and that is Hooke's law. So the relationship between stress and strain is linear, okay? The linear part there. So that relationship there, where we have the stress and the strain relationship being linear, we can apply Hooke's law. Okay, and that's the formula for Hooke's law. Sigma is equal to Young's modulus of elasticity multiplied by strain. The epsilon there, the smaller e, the epsilon is the strain, the symbol for strain. Okay, so where E is a measure of the inherent stiffness of a material, and its value differs for different materials. So of course we agree that some materials are more elastic than others. Huh? One of the most non-elastic materials, if there's such an expression, is actually ceramics. Your breakable plates. Try applying tensile forces on it. Do you think it's going to enter a plastic region? I mean, is it going to have like a really long elastic region? No, it won't, isn't it?
No, it won't.
Even the plastic region actually won't be there. Permanent deformation. Have you ever seen you know, you look at your plate, you're like, okay, this ceramic plate used to be much smaller than it is now.
No.
There's no such thing, eh? So you find that ceramics have almost no plastic region. So what happens is that, let me go back to the curve. What happens is that right here, okay, where you have the U's there, the fracture happens, okay? So this point actually is here. Oh, this is not there. So you just after the U there, just after the yield point there, where now the material yields to the stress, it actually immediately snaps. It doesn't even have to go through this whole thing. Okay, that's the difference. And the more the material is able to, the more the material is able to go through this process, the plastic region, okay, determines the toughness of a material. Metals are known to be tough because of this, okay? After succumbing to the stress, but they're still able to hold on before fracture, okay? There's still a period of time that passes before they actually fracture. So this area below the plastic region is what is known as the toughness. That's what determines or helps us determine the toughness of the material, the area under the plastic region. So for materials that do not have that, okay, so those are certain properties that they're devoid of. Some materials will have a shorter elastic region. Okay, it just comes a bit there, and then maybe they'll have a much longer plastic region. Okay, so that also tells us about certain properties that they have also. So we'll look at those as we go. Where will we? On slide 19. Okay, so this is the formula that we're going to work with. So for compression and torsional forces, this is the formula that we apply, where the tau is shear stress, the G is the shear modulus, and the what's this? Sigma or gamma? Gamma. Shear strain. Okay. But anyway, our main area of interest is here. I need you to know this. It will make sense more when we begin our calculations. Yield point marks the beginning of permanent deformation. The stress-strain relationship is no longer guided by Hooke's law. Okay, after the yield point, it means that the linearity is gone. Okay, the linearity that happens between the stress and the strain, it's gone. You're now in the plastic region. That's what it means. So this stress-strain relationship is no longer guided by Hooke's law. And as the load is decreased beyond Y, elongation proceeds at a much faster rate than before, causing the slope of the curve to change dramatically. What else here is worth noting? Elongation is applied by uniform reduction in cross-sectional area. We looked at this, consistent with maintaining constant volume. Okay, the volume is being maintained. What is volume?
Space occupied of the substance.
So that one is being maintained. Finally, the applied load F reaches a maximum value. And engineering stress at this point is called the tensile strength, TS, or ultimate tensile strength. So it will either be symbolized as TS or UTS. So TS or UTS is equal to force over. Remember I said all stress is equal to force over area. What changes is the type of force depending on the type of stress that you're looking for. So in this case, if you're looking for total strength, you look for the maximum force, okay? When you're looking for the ultimate tensile strength, you look for the maximum force applied on that specimen divided by the original cross-section area. So where is the UTS on the curve? Let's come here. UTS or TS is this point here. You are applying stress or applying force. That's the maximum that you apply, after which the downward curve happens. So that is our TS. So you get this value, the force that happens here, okay? The force at the TS is what you find there. For you to find the TS itself, okay? You get the force at max over that one. So in this case, in this graph, where this is already stress, it simply means that when you plot those dotted lines there, this value you're getting here is already in newtons per millimeter squared. For example, this is already the UTS, no need for you to calculate. But in the case where you have force against extension, that's a common one we like to use. Now that's where you get that force, okay? And then now you apply it in that formula, in this formula here. Original cross-sectional area will be given in the question. Okay, so there's also what is known as the Poisson ratio. This is named after a French engineer. This is basically lateral strain over axial strain. So I will not dwell much on this for the sake of, I know I've told you that this is in the test, so I will not bring this. But you still look into it. So there's the lateral forces over the axial, the lateral strain over the axial strain. Okay, and that's the symbol for the ratio. So that's the strain in the direction of the load over strain at the right angle to the load. And the ratio is according to this Young's modulus. Young again was is a scientist, after which this capital E was named after, elongation here in this case. So ductility measure is equal to elongation. So when we want to find the ductility, do you remember what ductility is? Ductility is the opposite of what's this word? What is ductility the opposite of? The word is gone. When something is brittle, yes, brittleness. So we understand what brittleness is, isn't it?
Opposite of elasticity.
Yes. No, wait. Ductility is in a way elasticity. So when something is brittleness is the opposite of ductility. So when something is brittle, it means that it has no elasticity in it, isn't it? It crumbles, or it breaks when some forces are applied to it. It doesn't really have that elasticity property in it. But ductility has that in it. Okay. So how do we calculate for elongation here? It's the length at fracture. Remember that after you have that snapping happen, when you join back your pieces together, you get your LF, which is the length at just before fracture, minus original length over original length. Okay, multiplied by 100 if you want it in percent form. So LF is measured as a distance between, oh yeah, this one we already looked at. So that is what elongation is. So the question sometimes will require you to find elongation. So that's a formula that you have to work with. So this is how a question would look like. Okay, let's read through the question. A tensile test uses a test specimen that has a gauge length of 50 millimeters and an area of 200 millimeters squared. During the test, the specimen yields under a load of 98 kilonewtons. The corresponding gauge length is equal to 50.23 millimeters. This is the 0.2% yield point. The maximum load is equal to 168,000 newtons. Is reached at a gauge length equal to 64.2 millimeters. Determine A, yield strength, B, percentage elongation, C, modulus of elasticity, and D, tensile strength. So I want you to look at this example. So let me just give you the understanding. You can calculate it yourself. We only have 10 minutes left. So this is the gauge length. Okay, so this is the L0. Okay, has a gauge length of 50 millimeters and an area of 200 millimeters squared. So this is your L0. Okay, and this is your cross-sectional area, A0. During the test, comma, the specimen yields under a load of 98 kilonewtons. Okay, so this is the force at the yield point is what? 98 kilonewtons. So for mechanical, for this question, it's just the English. Just the English is what we follow. So meaning at the yield point, that's the force, isn't it? 98 kilonewtons. Full stop. The corresponding gauge length is equal to, at the yield point, this is the corresponding gauge length. This is L1 now. Okay, this was L0, this is L1. So what have you noticed? There's an increase in length, isn't it? That has happened. Initially it was 50, just 50 flat millimeters. Now the length has extended to what? 50.23
2, 3.
millimeters, isn't it? So there's been
Yes, madam.
that slight difference. This is the 0.2% yield point you've been given there. The maximum loads, so F max, okay, or the TS there, isn't it? The force at the
Excuse me, madam.
maximum stress is
Excuse me, madam.
168,000, yes?
I don't know if I'm the only one who is not seeing what you are sharing.
Can I get a confirmation from anyone if they're seeing my slides?
It could be the only one.
I'm able to see it.
I'm
Maybe you
able
need-
to see it.
So if you cannot see it, maybe just quickly log out and log in, you'll see it.
Okay, madam.
Yes. Okay, so the maximum loads. Okay, this is the force at the TS, at the tensile. The maximum tensile strength there is reached at a gauge length of 64.2 millimeters. Then the question says, determine yield strength. How do you find yield strength? Remember what I said for stress, strength, stress, same thing. The formula is the same. It's always force over area. Okay. So for yield strength, what are you going to aim for? You're going to get the force at the yield point, which you've been guided here to say the specimen yields under a load of 98 kN. So you're going to get this one is going to be your numerator, isn't it? The F at Y. It has it will have a Y there to indicate that it's a force at the yield point. 98. So you convert this to newtons. So what do you get when you convert 98 to newtons?
98,000.
98,000, yes. So what do you have in the denominator?
$200.
200 maybe.
200. Yes, you have 200. Percentage elongation. So 98,000 divided by 200. Your answer will be newtons per millimeter squared or megapascal. So 1 Newton per millimeter squared is equal to 1 megapascal. Okay, they are the same in weight. We come to percentage elongation. Let's have one more, then you do these others. Percentage elongation, where were we? Slide. LF minus L0 over L0. Let's find now if we can find those ones here. What values are we using?
I think we'll use 0. For percentage, we use 0.2.
Good, madam. We use the 64.2.
Okay. Yes, minus,
4.2 minus 50.
yes, divided by, divided by 50, isn't it? And then you multiply everything by 100. Modulus of elasticity, you have
Yes,
the
madam.
modulus of elasticity, we have the formula somewhere. Tensile strength,
Kindly,
you have
Madam, kindly repeat on percentage elongation. The values for the formula.
64.2 minus 50 divided by 50. So numerator
so you
54.2 minus 50 millimeters, then the denominator is 50 millimeters, then you'll multiply everything by 100%.
So you subtract from the final elongation
Mm-hmm.
from the initial and the I mean,
Yes,
the first.
yes.
Okay.
So you're trying, what is percentage elongation? You're trying to say, okay, by how far has this specimen elongated? Eh? So you've been given the
Sure.
initial one, isn't it? So by the time you're done with the test, the L that you've been given is this one, isn't it? So you're trying to find the ratio, okay, of the change of length of your specimen. So you had 50 and then now you have 64. So it will be 64 minus 50 divided by 50 multiplied by 100. Or delta L over initial L or original L. Modulus of elasticity, you have the formula. It's in the notes. Tensile strength, you already have, you know which F to use for this one. So I think that's it. Try and solve this one by yourself. And then we'll look at, we'll continue next week. Hoping, so please continue looking at this material. I'll send you the slides. So at least we just quickly cover quickly so that we start space diagrams. We still have a lot of topics actually to cover. And time doesn't seem to be on our side. So cover as much as you can independently or in your own time, okay, so that we just more like revise. Like I said, there's a lot of data everywhere. There's the internet, there's YouTube, there's so many tutorials, like hundreds and hundreds. You just pick whichever one you feel you understand better. And the exercises, you just Google and they'll come. Others will even have answers, so you can actually practice, okay, like that, where you even mark yourself. That would be very helpful for you. Okay. All right, so I think we can call it an evening.
Madam, before you go,
Yes.
the network was very bad. I didn't hear what the answer was to my question. What makes the load to reduce at necking? What chemistry is there? What happens to the
What
faucet?
happens there basically is that as the necking begins, the cross-sectional area begins to become
To reduce.
to reduce, yes. Okay, so meaning the force applied now becomes less because of the cross-sectional area that has reduced.
Okay.
Yes, that's the understanding there.
All right,
That's
madam.
where that reduction is seen. All right then, have a good night. We shall meet next week again on Thursday.
Thank you, madam. Good night.
Okay, good night.
Thank you.
Good night.
Good night.
You. Good night, madam.
All right, have a good night.